In this video lecture, we're going to go over some information about records, arrays, and pointers, some of which you may be familiar with, some of which you may not. And the information contained in this lecture can be found in sections 7.3, 7.4, and 7.7 of the textbook. I do not have a set of written notes for this particular lecture. So we'll start with records and variants, which are also called unions. So as you've probably been told, records are usually laid out contiguously, but they may have holes in them for alignment reasons. So as an example, let's say we have this C++ declaration for a record. So it has a name which is 2 bytes, an atomic number which is an int, we'll assume is 4 bytes, a double for atomic weight which we'll assume is 8 bytes, and a bool for metallic which we'll assume is 1 byte. So if we lay it out the way it's specified in C and C++, which is that the compiler is not allowed to rearrange the fields to pack it more tightly, you'll see an arrangement something like this. Name will take up the first 2 bytes. But then, because atomic number has to be on a word boundary, the next 2 bytes are empty, and that's grayed out. So then atomic number is laid in, and it's 4 bytes. And then we have atomic weight right here, which is 8 bytes. The dashed line is just indicating the top 4 and the bottom 4 bytes. And finally, metallic is a bool. It's a single byte, and that leads to 3 more bytes of wasted space. So there's actually 5 bytes of wasted space in this record. And as I said, C and C++ specify that the compiler is not allowed to realign these or order the fields in order to save space. Now there's other languages like Pascal that would allow you to do it. In fact, in Pascal, you can tell it to pack the record to get the most efficient storage possible, and it can often, it will smash the fields together, but they will no longer be aligned on word boundaries. So here you can see that name takes the first 2 bytes, then atomic is taking the next 4, so it goes here's 2, and then here's 2 more, then atomic weight gets 2 bytes here, 4 bytes here, and 2 bytes here, and finally metallic gets 1 byte here. So it's packed very efficiently, but now access to the fields is going to be very inefficient because most machine language instructions assume that they're going to be doing their accesses on word boundaries, or in the case of doubles, on double word boundaries. So this would be much slower. So instead of completely packing it, some compilers simply are allowed to reorder fields as much as they can, even though there still may be some holes in them, but they're still going to respect word and double word boundaries. So here's perhaps the most logical rearrangement. We just move metallic up to occupy one of the 2 unused bytes next to name, and now we go from 5 wasted bytes to only a single wasted byte. And the reason that C and C++ don't allow for a rearrangement of the fields is they were designed as systems programming languages, and it turns out that they want to be able to assure the programmer that if they lay out a record in a certain way, that they can be guaranteed the fields will be mapped in that way. Because they sometimes may go into the records and do these non-converting casts or other things, and in that case they need to be absolutely sure that the fields have been laid out the way that they specified them. Okay, so as an example, if I had specified, if I want to go in and do a non-converting cast on atomic weight to just get at its significant bits for doing integer arithmetic, I really need to know that atomic weight is at a certain place in the record and that the compiler hasn't rearranged it. Okay, so that's simply what this point right here is making. Now, in certain languages, none that we have seen thus far, C, C++, and Java don't do it, but there's certain languages where you could have records with dynamic arrays. So you might be able to say something like class int n, and perhaps you could have int data n, and that's considered a dynamic array because you don't know until runtime how big that record is going to be. Now, most languages don't allow it in part because it causes implementation problems. You can't at runtime or at compile time know how much space to allocate to that class. And then this is a point we touched on in a previous video lecture, which is that unions are nice in their flexibility because they allow several different types of records to occupy the same memory space, but they cause problems for type checking because at compile time you can be never sure which type of record is actually currently occupying that space, and hence you can't type check the operation. And the lack of the tag simply is that the tag in some languages is attached to the union at runtime, so they can do dynamic runtime type checking to make sure that you're not doing something wrong. Now, C and C++ do not associate a tag with a record at runtime. They don't do any kind of dynamic runtime checking, but a language like Pascal does associate a tag with a variant record so that it can do runtime type checking. So the next topic is arrays, and as you know, they group a homogeneous set of data, and you can think of them as mapping an index type to a certain element type. And when talking about an array, there's three concepts: the number of dimensions, the bounds, and the allocation. Now, in C, C++, and Java, the lower bounds always start at 0, but that's not true in all languages. For example, Fortran allows the programmer to specify lower and upper bounds. And then allocation refers to whether they can be allocated on the stack, whether they have to be allocated from the heap, or actually whether they can be stored in a global area because perhaps they're a global variable. So you see here three different possibilities. The first is global lifetime and static shape. And that means that it's a global variable, statically declared, so you can put the array into a globals area, and it exists for the length of the program. If it's declared statically in a function, then we say it has local lifetime. It exists for the scope of the function, in which case we would put it into the function stack frame. And that stack frame, when it's deallocated, the array gets deallocated. And then you might also have a local lifetime, but the shape is bound at what's called elaboration time, meaning it's not until the function actually executes that we know how big the array is going to be. And in fact, the C11 standard has introduced such arrays. You can now say something like this in C and C++. You can say int, say count, and you can say int n, and then you could have, for example, int data n, and that's a dynamic array. Its size is not known until you actually execute the function, and each execution of the function may have a different size array. So we say the shape is bound at elaboration time, and by shape we mean in this case it's a one-dimensional array, but it could be a two-dimensional array. I could have said nn, in which case its shape again would not be known until we elaborate it. So these types of dynamic arrays pose certain implementation issues. They're not insurmountable. So again, I'm sorry, it wasn't in C11, it's in C99 that the definition was actually added for dynamic arrays. So what happens is the compiler will keep what's called a dope vector for an array. And that keeps track of the array's dimensions and its lower and upper bounds. So when allocating a stack frame, what happens is the fixed part of the stack frame, which is right here, is going to have room for a dope vector because you have to at least specify the number of dimensions. And then it will keep track of, the dope vector will keep track of the lower and upper bounds, and that won't be determined until runtime. So as you can see here in Ada, you can actually also dynamically specify the bounds. So you might not, in certain languages, even know what the lower bound is until runtime. And then in addition to the dope vector, it keeps a pointer to a variable size part of the stack frame. So we still don't allocate it off of the heap. We're still going to put it on the stack, just at the top of the stack, and we will point to that array through the pointer. So it won't be quite as efficient to access the elements, but we've traded a little efficiency for flexibility. So the next thing you need to be aware of is that arrays can be allocated in either column major or row major order. Row major is by far the most common. Only Fortran really organizes things in column major. So if you're wondering what that means, row major means that if let's say I have an array, and let's say that it is, in this case it's 10 by 10, then the first row is laid out contiguously. So that would be the elements in row 1. So this would be A0 in effect. And then all the elements in the column. This would be the elements in row 1. So that's row major. In contrast, when you do it in column major order, then the way that things get laid out is that this first element here is still A0, 0. But now the second element is actually A1, 0, so that all the elements in column 0 occupy the top row. Then all the elements in column 1 occupy the second row, and so on. And that's probably not as intuitive a way to think about it. Apparently the column major just came about because of some idiosyncratic ways of the original IBM architecture in which the first Fortran was implemented. But it's important to know what way an array is organized, because the way that you write your for loop should exploit the major order. So in C, I should write my loops using rows first. I should say something like row equals 0, row less than 9, row less than 10, row plus plus, and then my interior loop, or an internal loop, should be column equals 0, column less than 10, column plus plus. The reason I should do things this way is that when I now go through my array, I will first go through the first 10 items, then I'll go through the second 10 items, and because we typically bring in a set of things on a cache line, it will be much more efficient because the next element will already have been brought into the cache from memory. Whereas if I were to reverse this and do it in column major order, I would end up going here first, then here, then here, then here, and I might get a whole bunch of cache misses. If the rows are very big, I might get a whole bunch of cache misses which is going to slow down my program. And by the time I get up to here, this may no longer be in the cache, and I have to bring the whole thing back into cache. And so every access is a cache miss. You find your program runs much more slowly. So knowing the major order is important so that you write your loops in to take advantage of the major order. Now, you're also probably familiar with the fact that there's two common layout strategies for arrays. There's so-called contiguous elements and row pointers, and the easiest way to illustrate that is with this diagram. So in C or C++, I could write my array either this way for storing a set of days or this way. So in this first way, it's storing them contiguously. So when it lays it out, every single string has the same number of spaces, in this case 10. And you see that there's some wasted space. Whereas the other way is you can use a set of row pointers, which is what I've done right here. So now all I've allocated is a one-dimensional array of pointers to char stars. And now each entry points to a different set of memory, and you'll see that now there's no wasted space. If I'm allocating this off of the heap, or C++ will be smart enough perhaps to do that, you see that there is no wastage of space. So the advantage here with the row pointers is less wastage of space. The advantage here with the contiguous storage is much faster, not much, but faster execution, because you don't have to go through a pointer. Here, statically, you're going to be able to calculate the address of each element. If I say days 2 of 3, then I know at compile time how to calculate the address. It's essentially going to be days plus 2 times 10, because that's the length of each row, plus 3. Okay? Whereas over here at runtime or at compile time, I can't do that computation. I know that it's going to be an access through days plus 2, so I'll have to write it like that and then add 3 to it. And that's not going to be as efficient because I have an access through a pointer, and I'm not going to know this value right here until runtime. So it's a slower access. So that's the kind of difference between the two. Now, the advantage of row pointers is that they are much more efficient for storing things like matrices where the rows are of different lengths, or strings where the strings are a lot of different lengths. Now it does require some extra space for the pointers, but typically the pointers only take up 4 bytes, and we assume that the rows are of such different lengths that the space we waste on the pointers is more than made up for by the space we save on the rows. So the next thing we have to worry about with arrays when we're the compiler is how we calculate the addresses. And it's pretty easy in C, C++, and Java because they start their indexing at 0. But some languages like Fortran allow you to specify lower and upper bounds. And so that makes the computation a little more difficult. So we often break it into 2. So D stands for dimension here. So the number of elements in each dimension. So in the first dimension here, it's U upper bound 1 minus lower bound 1 plus 1. So if this was, for example, minus 5, and this was 8, then we'd have 8 minus 5 plus 1, or 14 elements here. So that gives us our dimensions. Then, to get the size of each so-called slice, we start from the inside out. So we start with the last dimension, which is this one. And we get the size there is just the size of whatever the element is. So we said array of element. Then for the second slice, so let's just set this up. This was a three-dimensional array. So we kind of have this situation right here, okay, roughly speaking. So what we're going for secondly is just a single row right here. So that's what S2 is giving me, is D3 times S3 is the length of this single kind of row. And then S1 equals D2 times S2. Now we're getting a whole plane in that array. And turns out we're not going to need to know the size of the whole array for our address calculations. So S3, the size of an element. S2, the size of a interior row. S2 and S1, the size of a plane, are what we need to know. So here you just kind of see, again, a kind of cube representing these things. So we might have the address of A starting here, and then we're having to somehow get at some element that is in the array. Okay, so continuing with the computation, if we have, let's say, the array variables I, j, and k, then what we would need to do in order to get their address is to say, okay, we start with the address of A, and then we need to know the size of the plane to get to the first one. So that's I times S1, plus then the size of that slice to get to S2, and then finally the size of the variable to get to S3. So going back here, what we're doing is, first of all, with the computation I times S1, let's say that I was right here, so we have to get up to this point in the array. So the I times S1 gets us up there. Then looking at I times S2, or j times S2, that's getting us somewhere. Let's say that j was right there. We have to be able to move this amount of space right here. So that is j times S2. And finally, to get to the right place, that's the k, we have to move this amount of space right there. Okay, and that is k times S3, hence that computation. Okay, and then we have to subtract off these lower bounds, and that's what that computation is. And the compiler, by being smart, can perform this computation at compile time, because those are all constants it knows at compile time. Whereas this right here is going to be computations it has to do at runtime. Okay, and finally, pointers and recursive types. There's really only one important point that I want to make with pointers, and it's this one right here, which is that pointers are used when you have a value model of variables. And what that a value model means is where you can have stack allocated objects. So when you can have stack allocated objects, you need to be able to make a distinction between stack allocated objects and heap objects, and therefore you have to have a notation like C does, where int a, well, even more, where say struct list node A means it is stack allocated, whereas struct list node star A means that we're going to be pointing to something presumably allocated off the heap, although we also could in a special situation, if this was B, say B equals ampersand A. We of course know that's dangerous because A can be deallocated and go out of scope on us, and that could be bad news. But at any rate, in a language like Java, where everything is allocated off the heap, that's a so-called reference model, and it no longer needs to have a notion of pointers because you don't have two different types of objects. You only have a single type of object.